Let's discuss one numerical problem from exercise 6.8. The reaction of ceramide with dioxygen was carried out in a bomb calorimeter, and delta U was found to be minus 742.7 kJ per mole at 298 Kelvin. Calculate enthalpy change for the reaction at 298 Kelvin. The reaction is given here. So when we look at this reaction, there is change in the number of moles, okay, between the reactants and product, okay. So this one is 1 mole, 3/2 mole, 1 mole, 1 mole, okay. Now what is given here? Given delta H is minus 742.7 kJ per mole. Now temperature is 298 Kelvin. Now what we are to find is this H, okay, delta H or enthalpy. So from this reaction, okay, before going to this reaction, we know that this delta H is equal to delta U plus delta Ng RT, okay. Now we have to find the change in the number of moles, okay, so between the reactant and product. So delta Ng so this means product, this means reactants, okay. So this N represents the number of moles. So in the product we will consider nitrogen and carbon dioxide, okay. This is liquid, okay, so we are going to consider these two. So 1 plus 1, 2 minus 1, so this will be, if we divide, it will be 1.5. so what we will get is minus 0.5. now we are going to add the values, okay, for this one. So delta H is minus 74.27 kJ per mole plus this one, so minus 0.5. R is, we know, this universal gas content, so it is at 0.314. so since it is kilojoule mole per Kelvin, okay, this is per Kelvin into 298 Kelvin. So T is this one, so this Kelvin and Kelvin we can cancel, this Kelvin and Kelvin will cancel. So what we'll get is 7.427 kilojoule per mole minus 1.2 kilojoule per mole. Now if you calculate this one, you will get this value, okay. So if you calculate, you will get 7.43 times 4 kilojoule mole per mole. Let's discuss the next topics. Enthalpy change, sorry, not this one, this one, okay. Reaction enthalpy. So what is reaction enthalpy? So enthalpy change involving during a reaction, okay, simply means reaction enthalpy, or okay, enthalpy change accompanying a reaction, okay. So the enthalpy change is given by this delta RH, okay, given by this symbol. So how you can find the enthalpy change or reaction enthalpy, okay. So it's given by delta RH, sum of enthalpies of product, sum of enthalpies of reactants, okay. So in example, taking this reaction, methane plus 1 mole of methane react with 2 mole of oxygen, okay, to give carbon dioxide, 1 mole of carbon dioxide and 2 mole of water molecule. So in simple way you can write it like this: enthalpy of carbon dioxide in the reactant product, enthalpy of carbon dioxide plus these 2 moles, so enthalpy of H2O, okay, minus the reactant enthalpy of methane plus enthalpy of oxygen, okay. So HM means molar enthalpy, okay. So since we are using moles, okay, number of moles, so we can write it as molar enthalpy, okay. We can denote this HM as molar enthalpy. Now next one, enthalpy of reaction. So this standard enthalpy of reaction, okay, is the enthalpy change, okay, enthalpy change for a reaction when all the participating substances are in their standard state. So this also similar with the first one, okay, enthalpy change of a reaction, okay, but in this case all the participating substances should be in their standard state. So what is standard state? Okay, so standard state means a substance at a specific temperature in its pure form at 1 bar pressure, okay. So standard state of a substance means it should be in pure form at 1 bar, okay, at a specific temperature. Example is ethanol at 298 Kelvin, 1 bar pressure, okay. So this is pure ethanol, okay, and then that means this ethanol is in standard state, okay, when it is in pure state at 298 Kelvin and 1 bar pressure. So usually, okay, data are taken at 298 Kelvin, okay, and this for standard enthalpy of reaction it is denoted by this one, delta H, this minus, okay. In this form we add this one, okay, delta H, or enthalpy we add this one, okay, to denote that it is a standard enthalpy, okay. Next one will be enthalpy change during phase transformation, okay. So during phase transformation, what will happen is changes in the phase will take place, like solid to liquid, or solid to vapor, okay, or liquid to gas, okay. All those transformation we'll see, and we'll discuss about their enthalpy change, that means heat involved, okay, in those phase transformation. Now first one, enthalpy of fusion or molar enthalpy of fusion, okay, denoted by delta FUS H minus. So the enthalpy change that accompanies melting of 1 mole of a substance in their standard state. So this standard state we have discussed, okay, that means at a specific temperature and 1 bar pressure. Now, so in this case 1 mole of a substance, okay, is melted, okay, like this one, ice to water, okay, or liquid, okay. So the delta FUS, okay, or enthalpy change is given by this one, the value is here, okay. So it's plus 6.00 kilojoule per mole. That means plus means this plus signs will denote that it is an endothermic reaction, okay, heat absorbed, that means, okay, in this process. And please note that in this kind of reaction the temperature and pressure are constant, okay, temperature constant, okay, at constant temperature this ice will melt, okay, the temperature will not change, okay, at constant temperature, and it will melt to liquid, okay. So in this case constant temperature and pressure will be kept, okay, for all this. Now standard enthalpy of vaporization, okay, or molar enthalpy of vaporization. The symbol is delta VAP H minus. So in this case amount of heat required to vaporize 1 mole, okay, 1 mole of a liquid at constant temperature and under standard pressure, that means 1 bar, okay. It's called standard enthalpy of vaporization or molar enthalpy of vaporization, okay. So heat required to, okay, convert this liquid into gas, okay, that means, and this should be at constant temperature and 1 bar pressure, okay. So the value here is, enthalpy change here is VAP delta VAP H plus, that means in this case also endothermic process, okay. The third one is standard enthalpy of sublimation, okay. So it is the change in enthalpy when 1 mole of a substance, okay, 1 mole of substance at constant temperature and under standard pressure, that means 1 bar, okay. So this sublimation means direct conversion of solid, okay, solid into vapor, okay, or we can say gas also, okay. So CO2 sublimes into CO2 gas, okay, or vapor, okay. So this is at 195 Kelvin, okay. So heat supplied, okay, and in this process also heat is absorbed, that's why this enthalpy is positive, okay, 25.2 kilojoule per mole, okay. So this magnitude, okay, of enthalpy change, okay, will depend on the intermolecular interaction, okay. So intermolecular interaction, that means stronger intermolecular reaction, higher enthalpy will be required, okay. Suppose water, so this water has stronger intermolecular interaction, or let's say attraction, okay. So it will require higher heat, okay, enthalpy, okay, compared to this acetone. So this enthalpy change will depend on the intermolecular interaction, okay. So this one, hydrogen bonding, it is a strong bond, okay, compared to this acetone, so this will have higher enthalpy, okay. So it will require higher heat to vaporize this water compared to acetone, okay, water and acetone. So higher heat we need to apply for this one to vaporize this water, less heat for this one as compared to water. Next one, standard enthalpy of formation, okay. So the standard enthalpy change for the formation of 1 mole of a compound from its element in their most stable state of aggregation is also known as reference state, is called standard molar enthalpy of formation, okay. So standard enthalpy, molar enthalpy of formation, denoted by delta FH minus, okay. So what this statement said that 1 mole of a compound will form from its elemental state, okay. So a compound should form from its elemental state, and that also should be in 1 mole, okay, and we call that as standard molar enthalpy of formation. So what is reference state, okay. So this reference state of an element is in its most stable state, okay, of aggregation at 25 degrees Celsius and 1 pressure, okay. So in this case the element should be in most stable state of aggregation, okay. Aggregation means combine, okay, 2 3 4 molecule, okay. That also should be in elemental state, okay, at 25 degrees Celsius and 1 bar pressure. Let's see this for better understanding. Example is reference state for hydrogen, okay. Dihydrogen is hydrogen gas, okay, and oxygen, dioxygen is O2 gas, okay, and carbon is graphite, okay. So we know carbon has other allotropes also, diamond, okay, coal, okay. These are the allotropes of carbon, okay. But among the allotropes, okay, of carbon, this graphite is the stable one, okay. So stable at 25 and 1 bar pressure, okay. So this is the reference state, okay, of carbon, okay. And this sulfur, okay, rhombic sulfur is the reference state, okay. It has also allotropes, okay, rhombic monoclinic sulfur, okay. So reference state, okay, in this case we'll take the reference state. Example is H2 gas, we are taking the reference state, okay. Hydrogen, the hydrogen, we are taking the reference state, that is gas. And oxygen, that is gas, okay, reference state, okay. And then so these two combine to give H2O, okay, liquid, okay. So in this case 1 mole combine with half mole of oxygen to give 1 mole, okay, 1 mole. And this graphite carbon, okay, solid, combine with the hydrogen, okay, to give methane, okay. So 1 mole of this combined with 2 mole of the hydrogen to give 1 mole, okay. Now let's see another case, okay. Suppose calcium oxide react with carbon dioxide, okay, 1 mole to give 1 mole of calcium carbonate. Please avoid the background noises, okay. So this calcium oxide, okay, this is in oxide form, okay. This Ca calcium is in oxide form, not in elemental form like this graphite, okay. So because it is not in elemental form but in oxide, okay, calcium oxide, so it is not the enthalpy of formation or standard enthalpy of formation, okay. So we are not denoting it by delta FH minus, but delta RH minus, okay. Now let's see another case. Hydrogen react with bromine to give hydrogen bromide. So these two combine to give 2 moles, okay. So since it's given 2 moles, it is also not considered as standard enthalpy of formation, okay. So we denote it by delta RH minus. Now in order to make it 1 mole, okay, we divide the coefficients, okay, by 2, okay. So half to give 1 mole, okay. So this is standard enthalpy of formation, okay. So we denote it by this, okay. And now minus sign indicates it is an exothermic process. Next is thermochemical equations. So thermochemical equation simply means a balanced chemical equation, okay, together with the value of its delta RH, okay, and enthalpy, okay, enthalpy of reaction is called as thermochemical equation. Now example is given, okay. C2H5OH, okay, ethanol react with oxygen to give carbon dioxide and water molecule. In this case 1 mole of ethanol react with 3 mole of oxygen, okay, to give 2 mole of carbon dioxide and 3 mole of water molecule, or water, let's say. So this delta RH, okay, refers to the number of moles of substance, okay. Now this delta RH, okay, will have this unit, okay, kilojoule per mole, okay. So please remember that. And all this process is taking place at constant temperature and pressure, okay. So that means at same, okay, temperature and pressure, this process or reaction is taking place. Now let's take 2 example, okay. This one, first this one, Fe2O3, okay, iron oxide, okay, or ferric oxide, plus free H2O to give iron, okay, and water. So this 1 mole of iron oxide react with 3 mole of hydrogen, dihydrogen, to give 2 mole of iron and 3 mole of water molecule. Okay, so in this case it is a exothermic process. Now let's see another case. Half, okay, mole of iron oxide react with 3/2 moles of dihydrogen to give 1 mole, okay, and 3/2 H2O, okay. So we are just dividing the coefficient with 2, 2, 2, okay. So what we get is delta FH minus S minus 16.6 kilojoule per mole, okay. And for here we get 33.3 minus 33.3 kilojoule per mole. In this case delta RH2 minus is half of delta RH1, okay. So this one is half of this one, okay. So in this case what I mean to say is it depends on the number of moles, okay. This one enthalpy, it depends on the number of moles present, okay, in the reaction, okay, how many moles we are using, okay. So since it depends on the number of moles, okay, this enthalpy is an extensive quantity, okay, extensive quantity. So it depends on the numbers, okay, of moles. Next one, let's see a law, okay, Hess law of constant heat summation, okay. So what did this law states? If a reaction takes place in several steps, then its standard reaction enthalpy is the sum of the standard enthalpies of the intermediate reaction into which the overall reactions may be divided. So please avoid those background noises, okay. Let's come here again. If a reaction takes place in several steps, then its standard reaction enthalpy is the sum of the standard enthalpies of the intermediate reactions into which the overall reactions may be divided at the same temperature, okay. So this means that a number of steps may involve in a reaction, okay, but the sum of all will be equal to the standard enthalpy, okay, of the reaction, okay. So this enthalpy, we know that it is a state function, okay. So since this enthalpy is a state function, it does not depend on the path, okay, but the initial and the final state, okay. Okay, so many background noises, but the initial and the final state, okay. So Hess law, okay, it explain that, okay, in other words, okay. So we will see some example for better understanding. This carbon, okay, or graphite react with oxygen to give carbon monoxide. Now 1 mole of this one react with half mole of oxygen to give carbon monoxide, okay. And here this delta RH, give it as question mark, okay. So we are going to find this one, okay. Now in this case, okay, CO is the major product, okay, but in actual case what we'll observe is some CO2, okay. CO2, some of CO2 is also produced in this reaction, okay, in actual case, okay. So it will be difficult to measure the enthalpy from this reaction only, okay, the exact enthalpy, okay. So we are going to consider other reactions, okay, involving similar species, okay, like this kind of reaction, okay, where carbon react with oxygen, okay, carbon react with 1 mole of oxygen to give carbon dioxide. Okay, and this enthalpy involved here is minus 393.5 kilojoule per mole. Okay, now we take this one as equation 1. Okay, and carbon monoxide react with half mole of oxygen to give carbon dioxide. Now we take this one as equation 2. The value is given here. Okay, next what we are going to do is we are going to bring this at the we are going to bring this carbon monoxide at the right side. Okay, so for this case we are going to reverse this reaction. Okay, this reaction, so we write CO2 to give CO and half oxygen. Okay, so in this case when the reaction is reversed, okay, please remember this, when the reaction is reversed the enthalpy change will be same. Okay, it will be same, only the sign will change. Okay, in this case, so when the reaction is reversed, this will be endothermic process. Okay, at first, before the reaction is, when the reaction is not reversed, it was exothermic process. Now when the reaction is reversed, it is endothermic process. Okay, but the enthalpy, okay, the energy, the heat involved will be same. Okay, we'll get the same enthalpy, 283.0 kilojoule per mole. So let's take it as equation 3. Now we add this equation 1 and equation 3. Okay, and we will get the desired equation. Okay, so just look at equation 1 and 3. Okay, so from 1 and 3, okay, for simplicity, I've not done the addition here, but for simplicity we can just cancel this one. Okay, from here we can cancel half, so only half oxygen will remain. Okay, so what remain in this reaction is this carbon, okay, half oxygen, okay, and CO, okay, CO. Okay, so we write the remaining part, okay, as this one. This will be the required, okay, equation. So carbon plus half O2 to give CO2. Okay, so when we cancel this one, okay, this will minus this one. Okay, first equation, delta RH of first equation with the delta RH of the second one. Okay, so we get this one. Okay, so this will be the enthalpy, okay, for this reaction. Okay, so we get this. Okay, so what, according to Hess law, okay, what Hess law is trying to say is, for the first case, A plus B. Okay, so this is delta RH. Okay, A plus B, we get enthalpy. Okay, we will get this enthalpy for A plus B. Okay, and then if we do subsequent steps, okay, or different steps, okay, but like delta RH1, okay, from C, delta RH2 to D, and then delta RH3 to B. Okay, that means these steps, okay, so 1, 2, 3 steps, it's giving B only. Okay, so the sum of all these will be equal to this one. Okay, this one only. Okay, the sum of all these will be what we are getting from here, what value of this one we are getting from, okay, from A to B. Okay, it will be equal to this sum. Okay, sum of all this will be equal to this one. Okay, so we write delta RH1 plus delta RH2 plus delta RH3, okay, is equal to delta RH. Okay, so this will take place at constant temperature. That means all these steps, okay, 2, 3 steps maybe, or 4 steps maybe, all these steps should be in constant or same temperature. Okay, now, so standard reaction enthalpy, okay, is the sum of the standard enthalpies of the intermediate reaction, okay, so in which the overall reactions may be divided at the same temperature, okay. So this is Hess law of constant heat summation.